The adversary has a budget too. Opening. The attacker you are actually facing. There's a version of cybersecurity thinking that imagines the attacker as an inexhaustible force. Patient, resourced, sophisticated, relentless. Nation-state level. Custom tooling. Zero-day exploits. Months of preparation. If this is the attacker you're designing against, the logical conclusion is that you can never truly stop them. You can only delay them. And that conclusion, while poetic, is also paralyzing. It leads to organizations either spending beyond their means chasing theoretical threats they will never face, or giving up on the engineering problem altogether because perfection feels unreachable. Here is the correction that changes everything. Attackers are not supernatural. They are economic actors. They have budgets. They have time constraints. They have skill ceilings. They have opportunity costs. When an attacker chooses to target your organization, they're making an investment decision. They are weighing the expected value of what they can extract against the estimated cost of extracting it. And when the cost of attacking you climbs higher than what they expect to gain, they do not persist indefinitely. They pivot. They find a softer target. They go where the return on investment is better. This realization is not a reason to relax. It is a design principle. If you understand that attackers have budgets, then your job shifts from the impossible task of building an impenetrable system to the very achievable task of making your environment expensive enough to attack that the math stops working in the attacker's favor. You're not trying to win a war. You're trying to make your battlefield unprofitable. Everything in this session flows from that idea. We're going to explore what it means to think about threats through the lens of economics, how to score and prioritize risk with that lens applied, how to design and implement controls that raise attacker cost rather than just block attacker access, and how to recognize when your detection and your intelligence systems are giving you a distorted picture of who you are actually fighting. The language of threat and cost. Getting the vocabulary right. Before we can talk about attacker economics, we need a shared vocabulary. For words get confused constantly, and the confusion leads to bad decisions. Those four words are threat, vulnerability, risk, and exposure. A threat is an actor or event with the potential to cause harm. It is external to your system. A ransomware group operating out of Eastern Europe is a threat. A disgruntled former employee is a threat. A misconfigured server that causes accidental data deletion is a threat. The threat does not need your system to be weak in order to exist. It exists independently. A vulnerability is a weakness in your system that could be exploited. An unpatched CV in your VPN software is a vulnerability. A default administrator password left unchanged is a vulnerability. An application that does not validate user input is a vulnerability. Vulnerabilities exist independently of whether anyone is currently trying to exploit them. A risk is the combination of the two. It is the probability that a specific threat will successfully exploit a specific vulnerability multiplied by the impact of that happening. This is where attacker economics enters the calculation. A vulnerability that is technically exploitable but requires 3 months of specialized research and $200,000 of tooling represents a very different risk profile than a vulnerability that can be exploited in 20 minutes using a freely available script. The vulnerability might be equally severe in terms of what it could expose. The risk is completely different because the attacker's cost is completely different. An exposure is the state of being vulnerable and visible. A server with an unpatched critical CV that faces the public internet is exposed. The same server, fully unpatched, but air-gapped from every external connection, is vulnerable but not exposed. Exposure is what converts a vulnerability from a theoretical concern into an actionable risk, because it is exposure that puts the vulnerability within reach of the attacker's budget. Understanding these distinctions is the foundation of how you score and prioritize work. It is also the foundation of how you argue for resources, which is a skill every security professional needs, because the business does not operate on theoretical threat models. It operates on risk conversations, and risk conversations require you to speak the language of likelihood, cost, and impact, not just the language of severity ratings. CVSS scores and the limits of severity without context. Every time a new vulnerability is published, it arrives with a number attached. The Common Vulnerability Scoring System, CVSS, assigns a base score from 0 to 10 to each CV. A score of 9 or above is critical. 7 to 8.9 is high. 4 to 6.9 is medium. Below 4 is low. The intention was to give defenders a consistent, vendor-neutral language for communicating severity. The problem is that CVSS scores are not risk scores. They are potential severity scores under idealized conditions. The base score is calculated from a set of factors: how the vulnerability is exploited, whether it requires network access, adjacent access, or physical access, whether user interaction is needed, what privileges are required, and then the impact on confidentiality, integrity, and availability if exploitation succeeds. These factors are assessed against the vulnerable component in isolation, without any knowledge of your environment, your compensating controls, or the attacker's actual capability. What this means in practice is that two vulnerabilities can share a CVSS score of 9.8 and represent wildly different levels of actual risk to two different organizations. A critical CV in a library that you use in an internet-facing application with no WAF in front of it and no input validation is genuinely critical. The same CV in a library that is embedded in a desktop tool used by 3 internal users on isolated workstations that have no external connectivity is technically the same severity score, but practically a fraction of a risk. The attacker's budget lens transforms how you use this information. When you are prioritizing a remediation queue, you are not sorting by CVSS score. You are sorting by the question of which vulnerabilities represent the best return on investment for an attacker who is targeting your specific environment. The questions you are asking are different. Is this vulnerability in a system that faces the internet? Is there a public exploit available? Or does exploitation require original research? Does exploiting this vulnerability give the attacker immediate access to sensitive data or privileged systems? Or does it give them a foothold in a quarantine zone with nothing valuable nearby? Has this vulnerability been seen in active exploitation campaigns in your industry? That last question is where threat intelligence connects to vulnerability management. The CISA Known Exploited Vulnerabilities Catalog, for example, maintains a running list of CVs that have been observed in active exploitation in the wild. A CV on that list with a CVSS score of 7 is more pressing than a CV with a score of 9.5 that has no public exploit and has never been seen used in the wild. The attacker who cannot afford to develop a novel exploit for the 9.5 vulnerability will absolutely use the commodity exploit for the 7. The economics of their operation dictate it. The practical implication is this. When a vendor tells you that a critical vulnerability in their product is unexploitable in your specific configuration, you do not dismiss the finding and you do not accept it at face value. You validate it. You ask, What exactly is the condition that makes it unexploitable? Is it a compensating control you have deployed? And if so, is that control monitored and tested to ensure it remains effective? Is it an architectural fact about your network that would need to change before exploitation became possible? And if so, do you have change control over that architecture? If the vendor's claim holds up under this scrutiny, you document the finding as conditionally accepted with the specific conditions named, dated, and attached to a review trigger. If any of those conditions change, the risk profile of that vulnerability changes with it. Designing controls that raise attacker cost. Understanding attacker economics is most powerful when it shapes how you design and select controls. The goal is not merely to block attacks. It is to make attacks more expensive than they are worth. There is a meaningful difference between these two objectives, and that difference shapes every architectural conversation. Consider the problem of phishing. A credential phishing campaign targeting your employees costs an attacker almost nothing to run. A phishing kit can be purchased for a few $100s. Sending 1,000,000 emails costs nearly nothing when using bulletproof hosting or compromised mail servers. If even a fraction of a percent of recipients click the link and enter their credentials, the campaign is profitable. The attacker's investment is low, the scaling cost is near zero, and the expected return, valid credentials to your environment, is high. Now think about what happens when you deploy hardware-based MFA using FIDO2 keys. The attacker successfully phishes the username and password. They try to use those credentials to log in. The login requires a hardware key that is physically in the possession of the user and cryptographically bound to the legitimate login origin. The attacker cannot replay the credential. Their phishing campaign, which was profitable at scale against password-only environments, produces nothing. The expected return drops to zero. The campaign against your organization is no longer worth running. Notice what happened there. You did not prevent the phishing email from being sent. You did not prevent the user from clicking it. You did not even prevent the credential from being stolen. You made the stolen credential worthless. You removed the return on investment from the attacker's campaign. That is raising attacker cost through architectural design. The same principle governs how you think about intrusion detection and lateral movement. When an attacker gains initial access to a network through a phishing payload, an exploited service, a compromised third party, their next phase is reconnaissance and lateral movement. They are mapping your environment, identifying valuable targets, and pivoting from the initial foothold toward them. This phase takes time. It requires trial and error. It exposes the attacker to detection. When you deploy an intrusion detection system inside your network, specifically positioned to monitor east-west traffic between segments rather than only north-south traffic at the perimeter, you are adding cost to the lateral movement phase. Every probe the attacker sends generates telemetry. Every failed connection attempt can become a detection signal. The attacker who knows that your internal network is instrumented must move more slowly and more carefully. Slow and careful costs time. Time costs money. And every additional minute of dwell time is a minute in which the attacker might be detected, contained, and ejected before they reach their objective. The placement of the IDS matters enormously for this reason. A sensor on the internet-facing perimeter only sees traffic entering and leaving. It tells you that someone is knocking at the door, but tells you nothing about what they are doing once they are inside. To add cost to the post-access phase, you need sensors inside the network on span ports or taps that mirror traffic between segments, positioned so that any host-to-host communication that is not part of the normal baseline generates a signal. Baselining is the prerequisite. You cannot detect anomalous lateral movement if you do not know what normal internal traffic looks like. Tools that impose economic friction. Every tool in your security stack can be evaluated through the lens of attacker cost. How much does this tool increase the price of attacking us? Let's walk through 4 of them with that question as the frame. Honeypots are perhaps the purest expression of attacker cost manipulation. A honeypot is a decoy resource, a fake server, a fake database, a fake set of credentials, placed in your environment and designed to look attractive to an attacker who is already inside. It is nothing legitimate. No real user ever accesses it. No real process ever touches it. Any interaction with a honeypot is, by definition, suspicious. When an attacker discovers it and engages with it, 2 things happen simultaneously. First, you get an alert with extremely high fidelity. The false positive rate is essentially 0 because nothing legitimate ever touches the honeypot. Second, the attacker is wasting time and resources on a target that yields nothing. Their reconnaissance is burning their clock, and in some configurations, their tools and infrastructure are being fingerprinted while they work. The cost and limitation of honeypots is equally important to understand. They are passive instruments. They do not prevent an attacker from reaching a real target. They only detect and delay. An attacker who never stumbles across the honeypot gains nothing from it and loses nothing to it. Honeypots are most effective in dense environments where the ratio of decoy targets to real targets is high enough that an attacker cannot easily avoid them during reconnaissance. And they require maintenance. A honeypot that has not been updated to reflect the rest of the environment's technology stack will be identified as a decoy by any moderately sophisticated attacker. Rate limiting on a WAF represents a different form of cost imposition. Automated attacks, credential stuffing, SQL injection scanning, content scraping are only economically viable because they are cheap to run at scale. A credential stuffing attack sends millions of login attempts using breached username-password pairs harvested from other data breaches. If even 0.5% of those pairs are valid at your site, the attacker has thousands of compromised accounts. The automation is the economic model. Rate limiting breaks the economic model by imposing a per-attempt cost through proxy rotation. When your WEF limits login attempts to a threshold that triggers a challenge or a block, the attacker must rotate through a large pool of proxy IPs to continue. Proxy pools cost money to maintain. As the required pool size grows, the cost of the attack climbs. At some threshold, the cost of proxy rotation exceeds the expected return from the compromised accounts, and the campaign is abandoned. The limitation of rate limiting alone is that sufficiently patient attackers can slow their rate to stay under the threshold while still systematically testing credentials over a longer time horizon. This is why rate limiting works best in combination with behavioral analysis that detects distributed, slow-velocity attacks from many source IPs that individually look benign but collectively form a pattern. EDR with behavioral anti-exploit capabilities raises attacker cost at the endpoint in a way that is particularly punishing for commodity malware operations. A commercial EDR solution with modern behavioral detection makes it extremely difficult to run standard exploit frameworks, commodity remote access tools, and well-known post-exploitation scripts without triggering an alert or an automated block. To bypass a modern EDR, an attacker needs custom tooling, either modified versions of existing tools that are not yet fingerprinted or purpose-built implants written specifically for that campaign. Custom tooling takes time and skill to develop. Time and skill cost money. A threat actor whose economic model depends on running the same toolkit against thousands of organizations finds that a properly configured EDR forces them to invest significantly more per target. Most commodity attackers do not do that. They move on to the targets where their standard toolkit still works. Building the program, vulnerability management as economic prioritization. Implementing a vulnerability management program is one of the most concrete expressions of attacker economics in action. Every decision in the program, what to scan, how to score, what to fix first, what to formally accept, is an economic decision about where attacker opportunity is concentrated and how to remove it efficiently. The program begins with asset discovery. You cannot manage vulnerabilities in systems you do not know exist. A scanner that only covers your known inventory is a scanner with a predictable blind spot, and blind spots are exactly where attackers look for the path of least resistance. Asset discovery must be continuous, not scheduled. Networks change. New services get deployed. Shadow IT gets connected. The asset inventory is a living document that decays the moment it is printed. Once assets are discovered and inventoried, the scanning phase begins. For network-connected systems, this means running an authenticated vulnerability scan that logs into each host and reads the installed software, patch levels, configuration settings, and running services. Unauthenticated scans miss a large proportion of findings because they can only observe what is visible from the network, open ports and banner responses, rather than what is actually installed and configured internally. The difference in coverage between authenticated and unauthenticated scanning is substantial enough that an organization running only unauthenticated scans should understand they are accepting a significant gap. After scanning comes prioritization, and this is where the economic lens is most critical. Raw scanner output for a medium-sized environment will contain hundreds or thousands of findings. Many of them will have high or critical CVSS scores. Attempting to remediate everything at once is not possible. Attempting to remediate in strict CVSS order produces a queue where a critical vulnerability in a rarely accessed internal tool is fixed before a medium vulnerability in an internet-facing payment processing application. That ordering is backwards from an attacker's perspective. The prioritization framework that actually reflects attacker economics combines CVSS base score as a starting point with 3 additional factors. The first is internet exposure. Vulnerabilities in systems directly reachable from the internet are prioritized above those in fully internal systems, because the attacker's access cost to reach an internet-facing system is near zero. The second is exploitation availability. Vulnerabilities with public exploit code, or that appear in the CISA-KV catalog, or that are referenced in active threat intelligence for your industry, are prioritized above those that remain theoretical. The third is asset criticality. Vulnerabilities in systems that handle sensitive data, manage authentication, or support critical business processes are prioritized above those in low-value systems, even when the CVSS scores are equal. Remediation tracking closes the loop. A vulnerability identified, scored, and prioritized is still open until it is patched and verified. The program must track each finding through its life cycle, from discovery to assigned owner to scheduled fix to verified remediation. It must escalate findings that age past their target remediation window. And it must produce metrics that show the business not just how many vulnerabilities exist, but how the remediation velocity compares to the rate of new vulnerability discovery, because that ratio determines whether the overall attack surface is growing or shrinking. When the intelligence is wrong, troubleshooting the signal. Good security operations depend on accurate intelligence. When the intelligence is wrong, when a threat that is not real is treated as active, or when a benign actor is misclassified as malicious, the consequences range from wasted analyst hours to reputational damage to customers receiving false alerts. Two scenarios are worth working through carefully. The first scenario involves a WAF that is not blocking SQL injection attacks that appear obvious in the logs. The WAF is deployed, licensed, and reportedly running. A penetration tester runs a standard SQL injection payload against your login form. The logs show the attempt. The application is vulnerable. The WAF did not block it. What do? The diagnostic starts with the simplest possible explanation, which is mode. Most WAF deployments start in detection-only mode, also called monitoring mode by design. In this mode, the WAF observes and logs, but does not block. This is intentional during initial deployment because a WAF in blocking mode with default rule sets will produce false positives that break legitimate application functionality until the rules are tuned. The question is whether someone deployed the WAF, configured the rule sets, and never moved it out of detection mode. Check the management console. Look at the operational mode setting. If it is in detection mode, that is your answer, but before you flip it to blocking mode, you must understand whether the rule set has been tuned. Switching to blocking mode on an untuned rule set in production will break things. If the WAF is in blocking mode and the injection is still getting through, the second check is rule coverage. WAF rule sets are not monolithic. They are organized into rule categories: SQL injection, XSS, command injection, scanner detection, and so on. Each category can be independently enabled or disabled. It is possible for the SQL injection rules to be disabled while the WAF is otherwise active. Review the enabled rule categories against the attack type you observed. If the rules are enabled and the WAF is in blocking mode, the third check is bypass. Some SQL injection payloads are specifically crafted to evade signature-based WAF rules by encoding the payload, splitting it across multiple parameters, or using database-specific syntax variations that the rule set does not cover. A standard payload like a single quote followed by or 1 equals 1 will be caught. A carefully obfuscated variant may not be. This is the hardest problem because it requires either updating the WAF rule set, adding custom rules for the specific bypass technique, or deploying additional application layer controls that do not rely on signature matching. The second scenario involves a campaign tracking system that flags an active threat campaign based on attacker session data from honeypot infrastructure. The report is distributed to customers in the financial sector, indicating that a coordinated campaign is targeting them. 3 days later, a customer security team calls to say that all of the activity attributed to the campaign matches the behavior of a known security research firm that conducts regular internet-wide scanning. The campaign is not an attacker. It is a scanner. How did this happen, and how do you prevent it from happening again? The root cause is almost always in the enrichment layer. Session data alone, IP addresses, commands observed, tools used, is ambiguous. An IP that sends SSH brute force attempts could be an attacker, or it could be a security scanner, a research honeypot operated by an academic institution, or a penetration testing firm. Without enrichment, you cannot tell them apart. The enrichment checks that should run before any session data is promoted to campaign intelligence include ASN classification, Major security research organizations operate out of recognizable ASNs, and these can be added to a known benign list. They include reverse DNS and WHOIS lookups that often reveal the operator of an IP range. They include cross-reference against scanner reputation databases, such as Shodan's scanning infrastructure list, gray noise, or commercial feeds that specifically catalog known research and scanner IPs. And they include behavioral consistency checks. A genuine attacker campaign typically shows purposeful progression from initial access attempts to follow-on exploitation, while a security scanner typically shows systematic, breadth-first probing without follow-through. The fix for the misclassification is not just correcting the current report. It is adding the enrichment gates to the pipeline so that future classifications cannot reach the distribution stage without passing through ASN verification, scanner database cross-reference, and behavioral consistency checks. Each gate is a cost, API rate limits, processing time, occasional ambiguous results that require manual review. The cost is worth paying because the alternative is distributing false intelligence that trains customers to distrust your reports. How three roles see the same economic principle differently. The idea that attackers have budgets plays out very differently depending on where you sit in the security organization. Three roles encounter it at genuinely different layers of the problem. The threat intelligence analyst lives closest to the attacker's budget as an observable fact. When they are building a campaign tracking system, they are essentially modeling the attacker's business operations. They are asking questions like, how long has this campaign been running? What tooling is being used? And is it commodity or custom? What verticals are being targeted? And is the targeting selective or opportunistic? How many IPs are involved in the infrastructure? And are they being rotated rapidly, which suggests high infrastructure budget, or are the same IPs persisting for weeks, which suggests low infrastructure investment and attacker confidence that they will not be blocked? The attacker's infrastructure choices reveal their economics. A sophisticated, well-funded threat actor buys freshly registered domains, deploys their C2 infrastructure on cloud providers using stolen payment cards, and rotates it every few days. Their detection footprint is minimal, and their infrastructure cost is high, but justified by their target value. A commodity criminal operation reuses the same bulletproof hosting provider, uses phishing kits purchased from a forum, and keeps infrastructure in place until it gets burned. Their cost is low, and their volume makes up for the lower success rate per attempt. When the threat intelligence analyst structures a campaign tracking system, they're building a model that captures these behavioral signatures over time. The baseline metrics they establish, average session duration, command diversity, tool fingerprints, infrastructure rotation frequency, define what normal looks like for known campaigns. An anomaly threshold is the point at which an activity cluster diverges from known benign patterns far enough to warrant promotion to active threat status. Setting that threshold is a calibration problem. Too low and every scanner triggers a campaign alert. Too high and genuine campaigns build activity for days before being caught. The detection engineer encounters attacker economics at the moment of designing alerts. Their specific challenge is that raising attacker cost through detection works best when the attacker does not know exactly which behaviors trigger alerts. If an attacker can cheaply probe your detection coverage, sending test payloads to see which ones fire an alert and which ones pass silently, they can map your blind spots and operate exclusively within them. The detection engineer's goal is therefore not just to detect known bad behaviors, but to make the cost of probing the detection surface high enough that doing so is itself suspicious. For SSH brute force alerts, specifically, a naive detection rule fires on any source IP that exceeds a fixed number of failed authentication attempts within a time window. This rule is easy to evade by spreading attempts across many source IPs, each sending only a few attempts. A multi-signal approach raises the attacker's evasion cost. Instead of one threshold on one signal, you weight several signals together. A single source IP with 10 failed attempts in 10 minutes scores medium confidence. The same source IP from an ASN known to host commodity scanning infrastructure with a HASSH fingerprint matching a known brute force tool, targeting a port that is not advertised in your DNS or external scan results, at 2 in the morning when no legitimate admin activity is expected. That combination scores high confidence even if the individual attempt count is low. To evade this rule, the attacker must change their tool fingerprint, use residential IP addresses instead of data center IPs, operate during business hours, and somehow know which ports you have left publicly visible. Each evasion step costs money or time or both. The security analyst at an MSSP encounters attacker economics most acutely in the conversation with customers about prioritization. When a customer's environment generates a long vulnerability list, the analyst's job is to translate that list into a prioritized action plan that reflects actual attacker interest in that customer's specific environment. An energy utility faces different attacker profiles than a retail e-commerce platform. An e-commerce platform faces different attacker profiles than a law firm. The vulnerabilities that represent the easiest, most profitable entry points for the threat actors most likely to target each vertical are not the same, and the MSSP analyst who treats all customers identically, sorting by CVSS score and emailing a remediation list, is not adding the economic intelligence layer that is the actual value of their role. Case scenario: the e-commerce platform under sustained scraping. Let us place everything we have covered into a scenario with real constraints and real stakes. You are the security lead for a mid-sized e-commerce platform. The company's competitive advantage is real-time pricing. The algorithm adjusts prices dynamically based on demand, inventory, and competitor pricing. For 3 quarters, a competitor has been scraping your product catalog and pricing data at scale, adjusting their own prices to match or undercut yours within minutes. The business has quantified the impact. Margin erosion on high-velocity SKUs is running at roughly 4%, translating to several $1 million per year. The executive team wants the scraping stopped. Here is the constraint that makes this a real problem rather than a textbook exercise. You cannot simply block all automated traffic. Your own legitimate use cases depend on automated access. Affiliate partners integrate with your catalog through programmatic access. Price comparison engines, the ones that drive significant inbound traffic, use automated crawlers. Your own mobile applications make API calls that look, from a traffic analysis perspective, similar to scraper behavior. A blunt block all bots policy would damage the legitimate traffic you want to preserve. The attacker's economics in this situation are important to understand before designing a response. Scraping your catalog costs the competitor almost nothing. They run a scraper script on cloud infrastructure that costs a few dollars per day. Every time you block their current IP range, they rotate to a new one. If you deploy simple IP-based blocking, you are in a spending competition you will lose because your engineering cost to maintain block lists vastly exceeds their cost to rotate IPs. This is a classic case where trying to block every attack vector is the wrong framing. The right framing is to manipulate the attacker's return on investment. The first architectural decision is to deploy a bot management platform that classifies traffic by behavioral fingerprint rather than by IP address. Legitimate browsers and mobile applications have consistent JavaScript execution profiles, navigation patterns, and timing characteristics. Scrapers, even sophisticated ones that use headless browsers, exhibit subtle behavioral differences. They tend to request pages in systematic sequences rather than following human-like navigation patterns. They execute JavaScript but do not trigger all the browser events a real user would generate, and they often request resources in a different order than a genuine browser render would. The bot management platform builds a confidence score for each session. High-confidence human traffic gets normal responses. High-confidence bot traffic enters a different treatment path. That treatment path is the second architectural decision, and it is where attacker economics becomes the explicit design principle. Rather than blocking the scrapers outright, which simply triggers their rotation to new infrastructure, you serve them deliberately degraded data. Product prices are returned with small random perturbations. Availability data shows items as temporarily out of stock when they are not. The scraper collects what appears to be valid catalog data. The competitor's pricing algorithm consumes that data. Their prices adjust based on incorrect information. The expected return from their scraping investment, accurate competitor pricing intelligence, is not delivered. The campaign, from their perspective, continues to work, but the output is worthless. They have no immediate signal that the data is corrupted. This approach has genuine costs and risks that must be named explicitly. The bot management platform subscription is not cheap. Misclassification, a legitimate affiliates crawler being flagged as malicious and serve corrupted prices, damages a business relationship that may be worth more than the scraping loss. A price comparison engine that consistently shows incorrect prices for your products will surface this discrepancy to human reviewers and eventually flag your platform as unreliable, damaging the organic traffic those engines drive. The mitigations for these risks are specific. You create a verified partner program with a documented API and high rate limits, specifically to give legitimate programmatic users a proper access channel that bypasses the bot detection logic. Every partner using this channel is authenticated with an API key, and their traffic is subject to terms of service that prohibit resale of pricing data. The malicious competitors cannot access the partner API because they cannot verify a legitimate business relationship. The legitimate affiliates have no reason to scrape because the partner API is better. Higher rate limits, more structured data, better reliability. The scraping problem is redirected to the economic channel where it can be managed contractually rather than technically. The final step is documentation of the residual risk. The scraping has not been eliminated. A sufficiently resourced and patient competitor could invest in evasion techniques sophisticated enough to fool the bot management behavioral analysis. But the cost of doing so, custom browser automation that passes behavioral fingerprinting, a pool of genuine residential IPs, human review of pricing data to detect corruption, is orders of magnitude higher than the cost of running a commodity scraper. The math has shifted. The business decision to accept the residual risk of highly sophisticated scraping, while having eliminated the cheap commodity scraping that was causing the actual margin erosion, is defensible, documented, and reviewed quarterly. Closing. What knowing their budget gives you. There's a freedom that comes from understanding your adversary as an economic actor rather than an inexhaustible force. It means you can stop asking whether your defenses are perfect and start asking whether they are expensive enough. It means you can look at a critical CVSS score and ask who would actually exploit this, what would cost them to do it, and what they would gain, rather than reflexively escalating every high number as an emergency. It means you can design controls that are not just technically capable of blocking attacks, but that specifically remove the return on investment from the categories of attack you are most likely to face. It also means you carry a responsibility to maintain intellectual honesty about which attacker you are actually designing against. Most organizations are not facing nation-state adversaries with unlimited budgets and multi-year patience. They are facing commodity criminal operations, opportunistic scanners, and financially motivated groups who are running a volume business and will abandon any target that stops being profitable. Designing and funding your security program around the theoretical nation-state adversary, when your actual threat profile is commodity crime, is its own kind of misallocation. It is spending your budget on the wrong fight. The discipline is to know the threat actors relevant to your environment, understand their economic constraints, and build a security posture that makes your environment a bad investment for them specifically. Not for every possible attacker, for the ones that are actually coming. When you can explain your security decisions in those terms, this control raises the attacker's cost past the point where attacking us is profitable. And here's how we know that. You have moved from compliance-driven security to risk-driven security. That distinction is visible in every conversation you have, every architecture you design, and every investigation you lead.